This example is found in the book of DAS. It helps the student to know how to analyze the retaining walls. The cross-section of a cantilever retaining wall is shown below. Calculate the factor of safety with respect to overturning, sliding, and bearing capacity. Use Rankine active theory. Gamma concrete is given equal to 23.58 kilonewton per meter cubic. In this example, the retaining wall is shown here. The type of the retaining wall is cantilever retaining wall, and we want to check the stability against overturning, sliding, and also the factor of safety with respect to the bearing capacity. The theory of active earth pressure is given here in the question to use Rankine active theory. The first step in calculating the factor of safety is to compute all the forces acts on the structure. First, we have to calculate the active earth pressure. The active earth pressure, we have to determine the type of the theory. The theory is Rankine, or since the friction between the wall and the backfill soil equal to 0, we have to use Rankine active theory. Since the backfill is the surface of the backfill here is tilted with the horizontal by an angle equal to 10 degree, we have to compute active earth pressure coefficient K active earth pressure coefficient by this equation: cosine beta multiplied by cosine beta, beta equal to 10. 10 is the angle between the tilted surface of the backfill with the horizontal line, minus square root cosine squared beta minus cosine squared phi. Phi is the angle of the angle of internal friction of the backfill soil here. Here phi equal to 30, and cosine beta plus, here minus and here plus. We get the active earth pressure coefficient equal to 0.3532. Then we have to compute the force. The force here is computed as a resultant of a distributed horizontal load. Here the H that is included in the resultant is computed from here at the edge of the retaining wall and extend the line, the vertical line, to this point with the tilted surface of the soil. Here the total H will be H1 plus H2 plus H3. H1 equal to 0.7. This is H1 or H3, 0.7, and H2 here, H2 equal to 6 meter. H2 equal to 6 meter, and H1, the height is computed from tan beta, tan 10 equal to H1 over this distance. This distance equal to 2.6. Here this is 2.6, and the angle here 10. So H1 will be equal to 2.6 tan 10 degree. Now multiplying, now P active equal to 0.5 gamma H square multiplied by K active. Gamma H gives us the vertical stress at any point. Here gamma H, since H equal to 0 at the surface, sigma vertical equal to 0. But here at this point, sigma vertical equal to H dash multiplied by gamma. This is the vertical stress, and here equal to 0. Here is the maximum value. Here is the maximum value, sigma vertical. If we want to compute the resultant, we have to use the area of this triangle. H gamma stress multiplied by, like the area of triangular, H dash gamma multiplied by H over 2. Therefore, P active equal to 1 over 2 gamma H multiplied by H multiplied by K active. K active transform the vertical load to horizontal load. Sigma vertical is vertical load. We speak about active horizontal load, so we have to multiply it by K active. Therefore, we have the active forces here, and the resultant is this. The resultant has an angle with the horizontal line equal to the same angle between the surface of the backfill and this line, also 10 degree. After computing P active, then P vertical can be obtained by multiplying PA by sine 10 and multiplying PA by cosine 10 gives us 158 pH, horizontal force. This force, the resultant, can be resolved into two forces, horizontal and vertical at this point. After that, after we computing the horizontal force or active forces, the resultant of active forces, we have to compute the forces from the weight of the concrete of the retaining walls. Here we have to divide the area into sub areas. Here, for example, the steam rectangular area here, number 1, and triangular area here, number 2, and the base rectangle area, number 3, and the soil above the base, number 4, and this soil also triangular soil, area of soil, number 5. 5 areas we have to compute them and multiply them by the area by for each area, multiply each area by the gamma of the concrete or gamma of the soil. So we have to construct this table. Section number 1, 2, 3, 4, 5. 5 sections. The area of, or the section number 1. The section number 1 here. The width equal to 0.5 and the height equal to 6 meters as they are given in this figure. 0.5 multiplied by 6 meter. 0.5 multiplied by 6 meter, the area will be 3. Multiplied by 1 vertical to the paper, we can get the volume. 3 multiplied by 1 equal to 3. This is the volume per meter vertical to the, or perpendicular with the paper. Section number 2. Section number 2 is a triangular. The height of the triangular is 6 meter and the width is 0.7 meter. 0.7 multiplied by 6 meter over 2. 0.5 multiplied by 6 multiplied by 0.2 or 0.7 here, 0.2. This is 0.2 as we used here, 0.2. The third section, third section, this is the third section, 0.7 the height multiplied by 2.6, 1.4 equal to 4. So here this is 0.7, should be 0.7. 4 multiplied by 0.7. Section 4. Section 4 is the width of the base, 2.6 meter width of the base, multiplied by the height. Height is 6 meter. This is section 4. Section 5. Section 5 is this distance, 2.6 tan 10 multiplied by 2.6 over 2. 0.5, 2.6 multiplied by 2.6 tan delta, tan 10, tan beta equal to 0.595. Now this area, after multiplication of the area by the weights, for example, unit weight, for example, section weight is a concrete material. So we have to use the unit weight of the concrete. Here we have to multiply 3 multiplied by 23 as it given, 23 in the question, 23.58. 23.58 multiplied by 3 gives us the weight 70.74. Section 2 also concrete, multiply it by 23.58 gives us this weight. Section 3 2.8 multiplied by 23.58. Section 4 is a soil. The type of the material is soil, so we have to multiply 15.6 by the unit weight of the soil. Unit weight of the soil as it given here, 18 kilonewton per meter cubic. Therefore the weight equal to 280 kilonewton per meter perpendicular to the paper. Here 0.595 also the area of soil, so we have to multiply it by the weight, by the unit weight of the soil. The arm from this is the weight. We will benefit and use these weight in the computing the factor of safeties. PV is the vertical force due to the active earth pressure. PV 158 PV, this is, sorry, Yes, the PV equal to 28 kilonewton here. The total weight we need the total weight. The total weight equal to 470. Also, we need to compute the moment of every force acts on the retaining wall. Therefore, we have to determine the arm from the center of the area to the point of the moment. Here, when we want to analyze the overturning, we assume that the retaining wall subjected to horizontal force here, to active force, and may make the structure overturning about this point. Therefore, we have to get to obtain the arm from the center of all the areas, or the section area here. For example, this section from this center to this point. The distance is 2.6 or 4.2. And from this section also, the center of this section to this point. This is the arm of the moment. And from this section also here. And from the section of the triangular to this point. So the arm of the section area, first section area, is 1.15, and the arm of the second, third, fourth, fifth, and even with respect to the PV equal to 4. To compute the resistance force, resistance moment, we have to multiply the weight by the arm. The weight, multiply the weight by the arm, gives us the moment, resistance moment. Here, resistance moment. And the total resistance moment equal to 1130. After completing and constructing this table, we start to compute the factor of safety against overturning. The factor of safety against overturning equal to summation of the resistance moment divided by the moment that caused the overturning. The moment that caused the overturning of the retaining wall, it comes from the horizontal force, active earth pressure. The resultant here, the horizontal force, make the structure overturning about this point. The moment in this direction, while, for example, the base, the moment of the base will be here, clockwise. And with respect to the clay here, the soil above the base, also in this direction. The weight here also in this direction. The weight of the triangular also in this direction. All of these moments are resistance moment, while this moment is M0, which caused the overturning. So we have, if we analyze the forces here and their effects about the overturning, we see that all the forces try to resist the overturning, except the horizontal force, which try to make the structure overturn about this point. So factor of safety against overturning, summation of resistance moment over the moment that will cause the overturning. Summation of the resistance moment is retrieved from this table here, 1130 over m naught equal to horizontal force multiplied by h over 3, since the resultants act at a distance equal to height of the triangular of the 3, h over 3, at a distance h over 3, 379 kilonewton per meter. Now factor of safety will be 2.95. A factor of safety is greater than 2, therefore it may be accepted. Now compute the factor of safety against sliding. Factor of safety against sliding equal to resisted forces and the force that try to make the structure slides. The horizontal force here, try to push the retaining wall in this side and make it slides here, but the friction between the base of the retaining wall and the soil try to resist this force. Always the factor of safety equal to resistance over the causes. The resistance here comes from Vt, the total weight of the structure, multiplied by angle of friction. Here, this is the base. In general, if there is force, try to slide the retaining wall here, example. And this retaining wall has a weight. This weight can be represented by perpendicular or vertical force. Multiply the vertical force or normal force by the friction, gives us by for example here tan phi, angle of internal friction. Here gives us a resistance friction try to resist this force. V total, as the weight of the retaining wall increases, the friction force also increases. Vt tan K phi. But here the delta, the friction, the angle of a friction here between the concrete and the soil equal to about 2/3 phi. Phi is the angle of the soil, angle of internal friction of the soil, 2/3 phi. K equal to 2/3 phi. Normal now the normal vertical multiplied by the friction unit here, by the friction coefficient of friction coefficient, plus the cohesion. Also the cohesion is another component contributes with this force to resist the applied force. The second force here can be computed based on the cohesion. Look, the cohesion is in kilonewton per meter square. multiply the cohesion by the width of the retaining wall, and 1 meter perpendicular to the paper. This is the second component, multiplied by K2. K2 also may be taken 2 over 3, just 2 over 3, 2 over 3, 2 over 3 multiplied by the cohesion. Since the cohesion between the concrete material and soil is not equal to the cohesion of the soil, and the angle of internal friction between the concrete and soil is not equal to the angle of internal friction of the soil. The first component here in the resistance forces, and this is the second component. The third component may be contributed in the resistance is the passive force here. Since there is a soil here, when the force try to slide the structure in this side, the passive force here try to resist, and the passive force can be obtained also from the using Rankine theory. But since here the surface is horizontal, the K active will be equal to 1 minus sine phi over 1 plus sine phi. P passive equal to 1 over 2 K passive gamma d square. D square is the height of the soil in the here in front of the retaining wall. The height is d plus 2 cohesion. If there's a cohesion here, cohesion will be included in the computation and in the computing P passive, and Kp equal to tan square 45 plus pi 2 over 2, or 1 minus sine phi over 1 plus sine phi. D equal to 1.5 meter. P passive equal to 1 over 2, 2.04 multiplied by 19 multiplied by 1.5 squared, plus 2 multiplied by 40 multiplied by square root 2.04 multiplied by 1.5. This equation can be used to compute the passive pressure or passive force when we base on the Rankine theory. Pa cosine alpha is the force that caused the sliding. The factor of safety will be computed according to this equation as we explained here. Gives us factor of safety equal to 2.7, which is greater than 2, greater than 1.5 may be accepted. In the third part, we have to check the bearing capacity. First, we compute the pressure distribution. The pressure distribution under the retaining wall can be calculated based on the following equation. Here the eccentricity equal to B over 2. B is the width of the retaining wall. B is the width of the retaining wall. B is the width of the retaining wall. Over 2 minus MR resistance moment, and M naught M naught is the cause moment that will make the overturn, make the retaining wall overturn, divided by the total weight of the structure. E will be 0.411 meter. Since it is less than B over 6, 0.411 less than 0.66. If it is greater than 0.66, it may be the pressure distribution under the base of the retaining wall. Some of this pressure may be in tension form. Q now can be calculated, the pressure distribution, summation of the vertical load over B, the width of the retaining wall, 1 plus minus, plus give us the pressure distribution under the retaining wall, equal to 190 if it is positive. If it is negative, will be 45.13. The stress distribution here, 190 kilonewton per meter square, and here 45. This is the stress distribution. The stress distribution at 2 of the retaining wall is 190, and at the heel equal to 445. Now we compute the ultimate bearing capacity according to the bearing capacity equation that we have learned in the previous course. In the first course, ultimate bearing capacity equal to CNC plus factor of safety related to depth, factor of safety related to inclination, inclined force, plus Q and Q also related to depth factor, related to inclination factor, here related to depth factor, related to inclination factor. Here the foundation here and the base of the retaining wall subjected to an inclined load in addition to the moment. Inclined in addition to the moment. To compute the ultimate bearing capacity, we have phi equal to 20. From this table, phi equal to 20, we get N sub C equal to 14 and NQ and N gamma equal to 5.39. So for phi equal to 20, NC equal to this table, this table, the number of this table is as in the book that we used. These tables are in different according to the book edition, according to the books edition. Now NQ equal to 6.4 and gamma equal to 5.39. Q equal to gamma multiplied by D, gamma of the soil 19, and D equal to 1.5. This gives us 28.5. 1.5 since the retaining wall here, the retaining wall, soil here above the retaining wall, above the base of the retaining wall is 1.5. Therefore, the base of the retaining wall, like the foundation, with a DF equal to 1.5. B dash equal to B minus 2E. This is the eccentricity, 0.406. B dash equal to 3.188. Now compute the depth factor and inclination factors according to this table. Depth factor F sub C D and QD equal to 1 minus F QD over NC tan phi square gives us this value, and FQ with respect to the second term to depth factor in the second term of the ultimate bearing capacity, we have to use this equation. In the third term of the ultimate bearing capacity, the factor related to the depth equal to 1. Inclination factor will be F in the first term, and the second term of the ultimate bearing capacity will be 1 minus psi over 90. Here psi equal to horizontal forces over vertical forces, tan inverse here vertical and horizontal. Vertical over horizontal gives us the value of psi. Inclination factor, and in the third term, hence the ultimate bearing capacity will be 40 C multiplied by NC multiplied by the factor related to depth and factor related to inclination plus Q multiplied by NQ multiplied by factor related to depth in the second term, factor related to the inclination in the second term, 1 over 2 gamma multiplied by N gamma multiplied by B dash multiplied by 0. Therefore, the result will be 569. This is the ultimate bearing capacity of the soil. Now, the ultimate bearing capacity represent the resistance, and the Q at the 2 of the retaining wall represents Q at 2 represents the applied force, applied pressure. Here the applied pressure, the maximum applied pressure will be 190 here. 190. This is the maximum applied pressure. To get the factor of safety, we have to use this equation. The ultimate bearing capacity of the soil divided by the applied pressure gives us 3, which is accepted value.